Welcome to the Simcenter FLOEFD 2020.1 What's New video. In this session, we'll explain the BCI-ROM and thermal netlist enhancements in FLOEFD 2020.1. Transient simulations can present a significant challenge in electronics thermal design. Modern electronics design requires consideration of multiple transient power loads, various power control strategies, and a wide range of expected operating conditions for the device. The computational time required to solve a full CFD model is often prohibitive, preventing the full transient design space from being explored. To address this problem, we introduced the capability to extract a boundary condition independent reduced order model, BCI-ROM for short, from a meshed conduction model. BCI-ROM technology allows linear conduction problems with any number of heat sources to be solved with similar accuracy as the full 3D CFD model, up to 40,000 times faster. A reduced order model is an alternative approach to extract a dynamic compact thermal model from a thermal simulation. A discretized computational model of an electronics device is a system of n equations that must be solved. The ROM extraction process aims to derive a reduced system of equations that will produce thermal results dramatically faster while maintaining the predictive accuracy in space and time. Let's see how we can extract the BCI-ROM model. Here we have an IGBT model with 12 heat sources represented by 6 diodes and 6 IGBTs. This is a conduction-only analysis, so no fluid or radiation is defined. We specified materials for all the components, and heat transfer coefficient boundary conditions at all the outer faces. The cold side boundary condition represents the side where a liquid cools our device, and the outer wall conditions represent sides communicating with the environment. We set 12 heat sources, and in the center of each source we place a monitor point as point goals. This is where the ROM model will output the temperature values. The model implemented is boundary condition independent, so you don't need to worry about the values of the sources and boundary conditions at the moment of extraction. What matters is the location of the conditions, the monitor points, and the mesh. Now we are ready to extract the ROM. We go to Tools, ROM Export. Here you set the extraction accuracy, and it is recommended to keep the default value. Then you define the maximum and minimum values for heat transfer coefficients, assuming that when you solve it, the real coefficients will be within this range. You check the exporting folder and click Run to export. Depending on the mesh resolution, number of conditions, and model complexity, the extraction may take from minutes to hours. As a result of the extraction, we create a set of matrices. The resulting ROM matrices can be solved in MATLAB or in GNU's Octave. You specify heat transfer coefficient exact values, initial temperatures, and power profiles, and get transient results in seconds. Another use of ROM technology is to convert a 3D task into a thermal netlist in SPICE format, which can be used by an electrothermal system simulation tool such as Mentor-Eldo or System Vision. Unlike BCI-ROM, the thermal netlist is boundary condition dependent, so when preparing the model for thermal netlist extraction, you need to specify exact values of the boundary conditions. To extract, you go to Tools, ROM Export. Select thermal netlist and define the relative accuracy of the method. Set the name and click Run to export. Let's summarize the benefits of BCI-ROM technology. BCI-ROM can solve linear conduction tasks up to 40,000 times faster without loss of accuracy. It is available for all CAD systems supported by FLOEFD. It is a boundary condition independent model. That means the exact values of boundary conditions are not used for extracting the model, but the range of possible heat transfer coefficients is specified. The exact values are input when solving the extracted ROM. Also, it allows converting a 3D task into a boundary condition dependent SPICE thermal netlist for an electrothermal system simulation. And finally, it enables the supply chain to hide sensitive IP contained within the detailed model. Thank you for your attention.